Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Okay. You can hear me in the other room, right? Okay. Today, I'm so glad that we can have our keynote speaker, our ultimate one, that will give us the keynote talk for this session. Distinguished Professor Eugenia Etkina from Graduate School of Education, Rutgers, the State University of New Jersey. Welcome, Eugenia. It's very nice to have you here. Finally, we planned about doing this maybe almost 2 years, right?
Right.
Okay.
Okay, yeah. I'm going to go share my screen.
I will introduce you first. You can you can share screen, but I would like to introduce you to the participants.
Go ahead.
So, who knows that I need glasses for this one? Eugenia Etkina is a distinguished professor at Rutgers, the State University of New Jersey. She holds a PhD in physics education from Moscow State Pedagogical University and has more than 35 years of experience teaching physics. She is a recipient of the 2014 Millikan Medal of the American Association of Physics Teachers, AAPT, awarded to educators who have made significant contributions to teaching physics, and is a fellow of the AAPT. Professor Etkina designed and now coordinates one of the largest programs in physics teacher preparation in the United States, conduct professional development for high school and university physics instructors, and participates in reforms to the undergraduate physics courses. In 1993, she developed a system in which students learn physics using processes that mirror scientific practice. That system, called the Investigative Science Learning Environment, or IL approach, can be used in physics course at any level, from middle school to graduate coursework. It engages students in learning physics by practicing it and improves their well-being. The IL approach serves as the basis for the textbook College Physics, Explore and Apply, and supporting active learning guide and instructor guide that are used in many universities and high schools for teaching algebra-based physics courses, especially advanced placement physics course. Since 2000, Professor Etkina has conducted over 130 workshops for physics instructors. She's a dedicated teacher and an active researcher who has published over 100 peer-reviewed articles. Without further ado, please welcome distinguished Professor Eugenia Etkina that will present Investigative Science Learning Environment IL, helping students learn physics by practicing it and be empowered in the process. Time is yours, Eugenia.
Thank you. Thank you, Rini, for the introduction. As Rini said, I work at Rutgers University. It's in New Jersey. It's a relatively small state on the East Coast. And I will be talking about the investigative science learning environment approach, how it helps students learn physics, and how it helps them enjoy learning it and develop the habits of mind that will be useful for them after they finish physics. So I will start with introduction of the term of physics education research. I'm sure you heard it before. More than 20 years ago, Richard Haig published a paper in the American Journal of Physics in which he compared the learning gains of 6,000 students. Some of them learned physics through traditional approach, when the professor lectures to the students and they take notes and then answer questions on the exams. And some of them learned through the interactive engagement, working in groups on activities. It turns out that while the learning gains of the students who learned through traditional instruction were almost non-existent, and non-existent means if you give students a pre-test and they score, let's say, 35% correct, after the instruction, they might score 36% correct on average, or 37. So they basically don't learn much in the course. The gains in the interactive engagement courses range from, let's say, 20% of a possible gain to up to 70% of a possible gain. And no traditionally taught course, students learned more than 20% of possible of what they could learn. So that was 22 years ago. Since then, there have been lots of studies in different disciplines, in engineering, biology, mathematics, and they all found the same thing. If the students are passively sitting and listening to a professor or a teacher lecturing to them, they don't learn much. Richard Hicks' study was repeated in 2016 with 50,000 students. And guess what? Same result. We do not learn on average from listening to our professors. We learn when we're actively engaged in constructing our own ideas, working in groups, talking to our peers, and presenting our ideas to each other. And this is not something that we need to question anymore. There's lots of data. It's like for Newton's second law. We don't need to question it. There has been no data that refuted it so far in certain conditions. And if we create the right conditions, we now know the students will learn. And if we don't create them, they won't learn. The question is, if we engage students in active learning, what should they learn? And this is a very interesting question, because if you look at traditional physics textbooks, their content did not change in the last, let's say, 100 years. So what students should be learning in the 21st century? Organization for Economic Cooperation and Development 2 years ago published a position paper about what knowledge, skills, attitudes, and values will the students need today to thrive and shape their world in the future. And what they said, that while the knowledge of the discipline will continue to be important, another type of knowledge is becoming more and more important for our progress. It is epistemic knowledge, or the knowledge about how the disciplines develop, or how do physicists come to know what they know? How do chemists come to know what they know? So this kind of knowledge will enable the students to learn after they finish our courses. And as you can see, in today's world, you cannot just finish university and be done with your learning. You need to be a lifelong learner. And that is only possible if you understand the epistemic nature of the discipline. In other words, where do all these laws that we have to memorize come from? Yeah. If you look at the Future of Jobs report, World Economic Forum, that was published in 2015, you can see that 5 years ago, the most important skills in workplace were complex problem solving, coordinating, and management. But in 2020, today, it is complex problem solving, critical thinking, and creativity. How can you develop creativity if you need to listen to somebody tell you what the right answer is? Or if there's only one right answer to a problem and somebody knows it? It's impossible. So we need to figure out what the students should learn. So I would say that there are several major challenges of today's physics education. First is, how do we engage all students at all levels of learning physics in the process of learning actively? How do we help them develop epistemic knowledge of the discipline? How to think like a physicist, as opposed what is Newton's second law? And finally, how to ensure that students do enjoy learning physics and want to pursue STEM careers. As a physics teacher, when I am, let's say, with friends at a party, or some new person meets me and asks, Eugenia, what do you do? And I say, I teach. They say, what do you teach? I say, well, I teach physics. They say, physics? Oh, you must be smart. Oh, I hated physics when I was in college or in high school. This reaction tells us that somehow learning of physics makes the majority of people feel stupid, not capable, and not able. They think that only geniuses and very special people can master physics, and that is a big problem. So that's why we're trying to change how people learn, what they learn, and how they feel about this learning. So why is this change is necessary? Well, you can Google anything. So you don't really need to know any facts anymore. You can always ask your computer and it will tell you. People can work with each other. Like here, I am talking to you in Indonesia, and there are people all over the world participating in this conference. This is something that we would not think would be possible even 5 years ago. But our collaboration and communication allows us to work with people all over the world. And the workplace does not require us to do the operations that are a mere repeat of what everybody else does. If you think about life in the 19th century, it was mostly agriculture. People were in the fields. That was the century of agriculture. The 20th century was the century of manufacturing. And so manufacturing occurred in factories. People stood at conveyors and repeatedly did the same operation. All they need for success is to follow instructions very well. None of this exists anymore. Everything that can be done on a conveyor is done by robots. And if you are hired to do a job, you need to be creative there. So following instructions will not get you very far. That's why the changes in the workplace demand that we change what we do. So, being very modest, I will say that the investigative science learning environment approach to learning and teaching physics will allow you to address these three challenges. I'm sure there are many other approaches, but I sincerely think that this is the most successful and advantageous if we want to conquer the difficulties of today's world. And you might be thinking, what is it, this investigative science learning environment approach, or ISLE? And ISLE means a small island in the sea of everything else. So we will start with a very simple example. Let me tell you what's going to happen. I will take a glass, a wine glass actually, and I will pour ice cold water into this glass. And what I want you to do, I want you to watch what happens. The water is really cold and it is a summer day. Think of what you are observing and how to say it in very simple words that a 5-year-old will understand. So what are you observing? What are you seeing?
There's water on the outside of the glass.
Yes. So the students will get in groups and they will look at the real glass, pour cold water. Each group will observe and agree that they all saw that there's water on the outside of the glass. So now the next question that the teacher will ask is, how do you explain where this water comes from? What I want you to do, and this is the request for students sitting in groups, usually around round tables or rectangular tables, I will say, come up with crazy ideas explaining where this water comes from. And the word crazy is necessary because the students need to be free in their thinking. Remember, we want to develop creativity. So what are possible ideas? Where can this water come from?
Can sip from the glass.
Yes. So it can sip through the glass. It comes from the water inside that I poured, right? Mm-hmm. Or it can go out from this water and settle on the outside. It can sip through or come from outside. The students also say that the glass, the material of the glass has water in it and it sweats.
Yeah.
Or where else can it come from?
It could be from the outside air.
From the outside air. These are usually 4 ideas that all students come up with. So what do? We have an observational experiment. We observe something, and students are familiar with it because everybody pours cold water on a summer day, touches the cup or the glass, and they feel it's wet. Now, what do you do as a scientist with all these crazy ideas? So we teach them that they need to test those ideas. And how do they test them? By coming up with new experiments whose outcomes they can predict using these ideas. So how can we test that water sips through the glass? What can we do?
We can try to make an empty glass, but make it cold.
Right. So we'll take an empty glass, and this is my fridge. You can see that what I eat, actually. So we put this glass into the fridge, and then if the water on the outside came from the water inside the glass, or it went out and settled, then if we take the glass out, it should not be wet because there's no water. Bam, the glass is wet. So what does it mean? It means that we rejected the idea that water sips through the glass or goes out from the top. Usually, in science, one experiment is not enough. So what other experiments can we run to reject sipping through the glass and going out? So the students suggest, for example, to pour a different liquid. For example, oil, cold oil into the glass. So if it is sipping or coming through the top, then there should be oil on the outside. And what do we see? If we touch the glass with cold oil, outside is still water. They also sometimes suggest to cover the glass so the water cannot come through the top and the glass is still wet. So all these experiments are suggested by students, and we usually do them right away in the classroom, or we have photos and videos. So now we rejected these 2, but now the other 2 are still left. The material of the glass sweats like we do in the summer. We go outside. There's water on the skin, right? We're sweating. Why can't the glass sweat? Or it comes from the outside air. The students get in groups again, and they start thinking about a new experiment. And they usually come up with the following experiment. So they said, okay, pour water into the glass and put it on the scale. If the water on the outside comes from the material of the glass, then the mass on the scale that the scale reads should stay the same or maybe even a little less. But if the water comes from the outside, then the mass should increase. So now they're making two different predictions based on two crazy ideas for the same experiment. Here we go. Watch the experiment. So here's an empty glass. We're pouring water in it, and the mass is 204 grams and 594 milligrams. Now we wait. It takes a little time. So what are you seeing?
It increases. The scale increases.
Yes, the reading on the scale increases. First, thousands of a gram, then hundreds, and oops, I didn't stop it at the right moment. Let me just drag it real fast. So you can see that it increased by, let me just stop it when it increases. It increases to but about 1/10 of a gram. 1/10 of a gram. So the mass increases. And this way, we can reject the idea that the glass sweats.
The glass sweats.
It definitely comes from the outside. And you might think, why is it important? Like, who cares where water comes from? It turns out that life of people in dry climates depends on knowing that they can collect water from the air. So this is water air dew harvesting system that provides safe drinking water to people living in dry climates. It's very simple. You know, it's just some collecting material and then a bottle in which water drips. And in the morning, you will collect a whole bottle of water. So it is a very practical thing. And it's very important to understand. And maybe you all knew before that water comes from the air. But the question is, how did you know? That is the difference between telling the students that, you know, air has water in it and it settles on the glass, as opposed to them figuring it out on their own. That's the epistemic knowledge that they develop. So what do we do to figure out where the water on the outside of the glass came from? We looked at the simple experiment, came up with crazy ideas, tested them, and rejected them one by one. And you might think, well, this is a relatively easy idea. What about a more difficult problem? So let's look at a more difficult problem. So we take a tank of water and we put a laser pointer above it. The green color is better. We put the tank of water on a piece of paper. And when we shine the laser on water, we will see this beautiful light cone. So where does this light cone come from? That is the question that students need to answer working in groups. They have one big aquarium and they have lots of little pieces of equipment on their desks. They have lasers, they have paper, they have small containers of water, they have pieces of glass, they have a lot of materials. So how do they approach this? So the first, they observe, as we observed the wet glass, and then they notice the paper. And they say, well, paper is the reason for the cone because it scatters the light of
the water,
of the laser. So the laser is shining and the paper scatters it into the water. So how can we test it? We take the paper, we put a little bit of chalk dust so we can see the scattering of light in the air, like we can see it in the water, and there's no cone. So it's not the paper. We reject the paper, so maybe it is glass. So we take aquarium, put it on the black surface, not on the white paper, and there's no cone. So it's not glass, not water. What else can it be? And then we notice that there is a little bit of air between the paper and the aquarium. So maybe it's the air that is responsible for the cone. How can we test that? The students say, well, if we just wet the paper, it will stick to the aquarium and there will be no air. So wet paper, no air, no cone. So how does the combination of the paper and air, which becomes now the most important part of the experiment here, in addition to the glass and water in the container, how does it do it? The students now have to explain what they found. And for this, they take we give them whiteboards on which they can draw and then lift these whiteboards. They are, about this size, and they write with markers, and then they lift their whiteboards and everybody in the class can see each group's whiteboard. So what do? They say, okay, if this is the paper and here, and this is the air, so this is the paper and this is the air, this is the glass, and this is water. The laser sends the ray which is scattered by the paper in all directions. The very last ray that is almost parallel to the surface of the container air will be refracted towards the normal in glass, and then will open up a little bit in water because the index of refraction is less of water than of glass. And because of this bending towards the normal, this ray that we can think is like the last most parallel ray will still bend inward and form this cone. It also tells us that if we take glass instead of water, a piece of glass with no water, then the angle of this cone will be less in glass only. So we can test this idea by taking the piece of glass and shining the same laser pointer in it. And you can see that in water, the cone is wider than in glass. So this is a complicated problem, but the students can solve it very successfully if they learned how to think this way, how to work in groups, share, argue, and present their results. So what do? They observe and notice. We posed a question, but we did not start with a question, and we did not ask the students to make any predictions before they observe. No predictions, no like, what do you think will happen? None of that. Mm-hmm. After they observe, they came up with an explanation. It was the paper. They ruled it out. They came up with an explanation. It was glass and water. They ruled it out. Then they came up with the idea it's the air, and they tested it, and then they explained why the combination of the paper, air, and glass and water produced the cone. And at this moment, when they're coming up with ideas, all ideas are welcome. Nobody feels stupid. All you need to do is figure out how to test it. So once we ruled with an idea that we could not rule out, we can now apply it for practical purposes. We analyze the system quantitatively. We can build something if we want, whatever we desire to do. But the point is that we go through the process together. And this togetherness makes the success much more abundant and common than when the students are working individually, because you probably know we're much smarter when we're together than when we're alone. And this process is the heart of the investigative science learning environment approach. To construct any idea, students start with simple observational experiments. They identify patterns in these experiments and come up with explanations, models, crazy ideas, hypotheses, whatever you want to call them. Then they need to design experiments, the testing experiments, for which they need to make predictions. But their predictions are not crazy ideas anymore. Their predictions are based on the explanations that they just constructed. And they're not testing their intuition. they're testing newly constructed explanations or models. So when, when they make these predictions and run the testing experiments, if the outcome of the experiment does not agree with the prediction, they need to think what to revise, whether we need to check assumptions. Maybe we assumed that something will work one way and it didn't, in addition to our model. Maybe we need to propose a new model, reject the old one, or maybe we should say, we didn't collect enough data to even come up with a model or explanation. So this revision is a complicated process that repeats multiple times, as you could see with the wet glass and with the light cone. But when the outcome matches the prediction, and we run more testing experiments, and eventually we say we cannot reject this explanation or this mathematical model, we proceed to application experiments. We build bridges, we launch satellites, we make computers and cell phones. These are all application experiments. So we have a book written about this approach. It's called Investigative Science Learning Environment. When the learning of physics mirrors doing of physics. It's published by the Institute of Physics. And we have, as Rini said, a textbook that people can use to learn physics this way. So there are certain things that are different in the ILE approach compared to traditional. When we teach physics, we usually think of the demos and labs. We show the demos as instructors, and students do labs, usually following our prescribed steps in the labs. So that is very different in ILE. All experiments that students observe or do themselves are grouped into 3 categories. Observational experiments, as you could see with the cone or the wet glass, testing experiments, and application experiments. For the wet glass, collecting water in a desert is an application experiment when you know where water comes from. I can give you a few examples. For example, students design an experiment to find a relation between a potential difference across a current through a commercial resistor. They do not know any relationships yet. They need to figure out this linear relationship that only works for a commercial resistor. Then they need to design an experiment to test whether this relation applies to an incandescent light bulb or an LED, and they will find that it doesn't. So they can say this relation only works for an incandescent bulb. And they can also design an experiment to use these relations to construct a circuit which can power an LED without overloading it. That is a very difficult problem, but you can only do it if you did the first and then second experiment. But it's more to the investigative science learning environment approach than the flow, the logical flow. As you could see, students could solve the light cone problem only if they can draw ray diagrams. Different representations other than algebra or calculus are very important to help students move from abstract words to abstract algebra or calculus. So these are graphical representations. And our approach uses them beginning from kinematics, motion diagrams, force diagrams. We have energy bar charts, momentum bar charts. We use energy bar charts not only in mechanics, but in thermodynamics, in static electricity, in quantum optics, in atomic physics, in nuclear physics. So it is a tool that helps students reason about using energy approach in any field of physics. But another important thing is that while constructing concepts, students work in groups. They work in small groups, and then they share what they came up with, forming a learning community. A learning community is probably the foundation of the ILE approach, because we're all in it together. We're going to help each other. We're going to challenge each other. And there are no smart and stupid people in the class. And in order to help those who learn at different paces, we give students opportunities to improve their work without punishment. If you took a quiz and you didn't do well on it, you can come and redo it. You get a different problem, you get a different question. But if you learned 3 days later or a week later, but you really learned, you get your full score. So you can improve your work without punishment for trying the second and sometimes third and fourth time. The ISLE approach is an example of an intentional approach to curriculum design. So what is intentionality? Intentionality means that the product of knowledge cannot and should not be separated from the means by which it came to be known. What does it mean? Well, imagine a traditional physics classroom. Students are sitting in rows. There's a guy in the front, usually a man. Often they wear glasses too. And this person says, today we're studying Newton's third law. Newton's third law says that when two objects interact, they exert forces on each other that are the same in magnitude and opposite in direction. And the students take notes. So the product of knowledge is Newton's third law, but the means by which it came to be known is authority. So if you present the material or information, as we like to say, to the students, they think that knowledge comes from authority, from the teacher or from the textbook. And if a student takes a test and doesn't do well on it and gets, let's say, 50% out of 100, we say, well, too bad, you didn't learn it, we are moving on. That is another means that sends a very strong message to the student that the timing is more important than learning. So we have two intentionalities in the ISLE approach. First, we want students to learn physics by practicing it, not from authority. And we also want their well-being to be enhanced while they're doing it. So they don't feel inadequate, not belonging, or not able to learn. So students learn physics by practicing it, and students develop confidence and growth mindset. So how do we know how physicists practice physics? And how do we know how to help students develop confidence and growth mindset? So we study history and philosophy of science. We observe physicists, and we study learning communities, motivation, confidence, and cognitive development. So an example from the history of science. If you look, for example, at the photoelectric effect, you can find that the scientists who contributed to its development went through exact same steps as we just went figuring out why the glasses went. They went through accidental observations, qualitative observational experiments, quantitative analysis, explanation by Einstein using assumptions from Planck, and then Millikan was testing the Einstein's equation, which eventually was applied to a myriad things, and one of them is a photo multiplier tube. So we can put all these people on the ISLE process. So historically, whatever you take, you can follow this sequence from observational experiments to possible explanations to testing experiments and practical applications. Do physicists work like this in real time? We find that they do indeed. So we gave this problem to a group of physicists. I'm hearing an echo. I wonder what's
going on. It's please don't. Maybe because it is unmute. You continue, Eugenia.
Yes.
It's fine now.
So we found groups of expert physicists who are actively publishing, put them in couples, and gave them the light cone problem. You can see how they're working on it. And what we found that first, they work together a lot. If you look at the graph, when one person is speaking, it's red color. When the other person is talking, it's this color. And when they're working together, continuously talking to each other, it's purple. Look how much purple is here. So they're working as a group, and then they go from observations to patterns to hypothesis to experimental design, predictions, experiment performing, and then again and again and again. And so we find that even in real time, physicists follow this process. It turns out that our brain also works this way. So right now, I am speaking and I hear an echo. That's a sensory part of my brain. I start thinking, what am I hearing? I just hear my voice again. I start thinking about it. Oh, it must be an echo because I'm familiar with an echo. And then I start thinking, what could this echo be? And I realized that somebody probably did not mute their microphone. So I tell my students, please mute your microphone. And this is the brain learning cycle. Comes from concrete experience to reflective observation. I hear my voice twice. So looks like an echo, an abstract hypothesis. Somebody doesn't have a muted microphone. So I tell them, please mute your microphone. The echo disappears, right? But I have to talk. I have to think. I have to talk, and I have to test my ideas. And so this brain cycle happens very quickly in our heads, but it's totally consistent with the IL process. So the cognitive science tells us that learning is a social process. People cannot learn alone. And when students have fixed mindset, and fixed mindset means, intelligence is given, I am a smart person and I'm a stupid person. So then if you think that that intelligence is fixed, you're not going to attempt difficult problems. You will study for grades, not for your own learning. And what is important, that perseverance is one of the major predictors of success in life. So do we need to teach this process to the students of figuring out things on their own, of persevering and working together? So if you have children or siblings, you probably saw this many times. Children eat dirt. Why would they eat dirt? Well, this is dirt. I observe dirt and I start thinking, looks like chocolate. So that's my reflective observation. Well, looks like chocolate. So when I eat it, will taste like chocolate. Bam, I test my hypothesis by trying it. So this is a natural process. And if you have small children around, watch them, you will see do them. We also know that the students will continue doing things for a long, long time until they succeed. If you see them skateboarding or biking or trying to play computer games, they work together, they persevere, and they continue doing it until they master it. So why? Why don't they do it in school? Many reasons. One of them, because they want to do it. They have the need to know. So why can't we do the same in school? For many reasons. But mostly it's because our traditional approach to teaching goes against everything that we know helps students learn. We give them answers before they have questions. They have no need to know. We give them grades without resubmission of work. We give them no opportunity to try without being afraid to fail. And when you are afraid to fail, you're not going to try. We preset the pace of the curriculum. We punish them for learning at a pace different from what we expect. We grade on a curve. We punish them for collaboration. We give them traditional problems on multiple choice tests. We punish them for needing to reason with tools other than mathematics. And for women, all these issues are much worse because they have very strong imposter syndrome. They already think they don't belong. And when all this is happening to them, they think, well, I don't belong for sure. So they do not work with other people and they do not form the community. So what is the solution? I would say that it is universal design for education. So what is universal design? I don't know if you know the term. It was developed in US by architects who realized that people who have physical impairments have difficulty functioning in the society because we're trying to fix people by giving them wheelchairs instead of fixing our buildings, instead of making the buildings accessible for everybody. So in US, in elevators, I don't know about Indonesia, but the buttons have this braille carving so a blind people can push a button. The sidewalks have ramps so a wheelchair can move smoothly. All buses have these lifting platforms for wheelchairs so a person in a wheelchair can use public transport. A blind person can walk on a sidewalk and feel the bumps when the sidewalk is ending. So the universal design says we don't need to fix the person who is having trouble. We need to fix the environment. So that's exactly what the aisle approach does. It fixes the environment for student learning so everybody can be successful. How does it fix it? Students learning through aisle approach start on the same page. They observe simple phenomena and they discuss them using simple language. So everybody starts at the same level. If you have the parents who are very educated and they taught you a lot, or you're coming from a place where nobody paid attention to you, when you see the glass with water, you see it's wet, right? We use representations to help, and they're really helping those who are struggling with algebra and calculus. Students discuss ideas together and test them right away, so nobody feels stupid. In fact, when the idea is rejected by the experiment, it's a victory because nothing can be proved, but disproved it can. Students progress at their own pace. They improve their work without punishment, and they're a part of a community with shared expertise, and they develop productive habits of mind. So starting on the same page and not using fancy language develops confidence. Using representations, discussing ideas helps the brain development. Progressing at your own pace, improving work without punishment develops growth mindset. Community shared expertise helps avoid imposter syndrome and sets up for success in life. So that's why it's a good thing. So these are IELTS students. And, they are high school students, middle school students, college students, and graduate school students. So you can learn an IELTS concept, any IELTS concept, in the same way as I showed you for the glass and for the light cone. For example, let's say we give students spring scales and we ask them to see what the spring scale read when one person pulls, both pull, or the other person pulls. And the students find, this is an observational experiment, that no matter who pulls the scales, different scales, spring scales with different markings, they read the same numbers for two people all the time. So the students draw a force diagram and come up with an idea that when scale 1 exerts a force on scale 2, the scale 2 exerts the force of the same magnitude on scale 1. So the hypothesis that they form, then when two objects interact, they exert forces on each other that are the same in magnitude and opposite in direction. Well, this is rather crazy, right? When a big truck collides with a small car, the small car is damaged much more. How can they exert the same forces? So we invite them to test this idea. And what they do, they have carts of different masses and force probes, and they try to, let the carts collide, and the force probes measure the forces that carts exert on each other, and they expect a heavier cart to exert a larger force, although their hypothesis predicts that they will always exert the same forces on each other, different in different experiments, but in the same experiment, they should be the same in magnitude. But the students don't believe in this hypothesis. They want to reject it naturally. And what they do, so here's the experiment. I will not show you the force probes. I'll show you the plungers that allow you to see how the carts are interacting. So this is the light cart, and this coming now is a heavy cart. I'll make it go slower. So this is the heavy cart that is loaded with a lot of heavy blocks. Look at the plungers. So one is stationary and light, and this is heavy and moving. Look at how plungers squeeze exactly the same way. So the red card pushes the blue card exactly the same way as the blue pushes the red until they separate. And so the students see on the computer screen these two forces that in time are always the same in magnitude. So they basically invent Newton's third law all by themselves, starting with the scales, going to cards, and doing tons of experiments trying to reject it, and they can't. And they do it using this lab handout when they do an observational experiment and then the testing experiment, exactly as I told you. Rini, we started a little later. How much more time do I have?
You still have, right now is 30 minutes.
Oh, okay. Okay, very good. Okay, so this is the lab handout, and you can see that the students start with an observational experiment and proceed to the testing experiment. Exactly what we did together. They get a handout, they work in groups, and they do these experiments and follow up with this reasoning. So we want them to develop scientific habits of mind. So what are the scientific habits of mind? We call them scientific abilities. We interviewed many physicists about what they do when they do physics. And we came up with a list of things that they do. They represent information in multiple ways. Sketches, graphs, Feynman diagrams, force diagrams, whatever, right? Design and conduct experiment to investigate a phenomenon. That's what we just did. Design and conduct a testing experiment to test a model hypothesis, explanation, or mathematical relation. Conducting application experiments, developing models, collecting and analyzing data, evaluating models, equations, solutions, and claims, and communication, and communicating scientific ideas. So now we want our students to develop these scientific abilities as they are learning physics, because we want them to develop epistemic knowledge. So what kinds of things can they do? Here's an example of a problem that the students work together in a group. An elevator is pulled upwards by a cable so that it moves at a constant upward speed. Maria draws the unlabeled force diagram. See, that's the system, the elevator, and these are two forces that she draws. And says, if the elevator is moving upward at a constant rate, the forces exerted on it must add to zero. Jose disagrees. Looking at the force diagram, he says, the way you've drawn the force diagram, the elevator will stop moving because there's no net force exerted on the elevator. So the students need to correctly label the diagram, what are those forces, and decide who they agree with, Maria or Jose. And for the statement you disagree with, how would you convince him or her that he or she is incorrect? So if you look at this problem, then it makes students represent phenomena, evaluate somebody's statements, and design an experiment to test the hypothesis, because you can only convince Jose that he is incorrect if you actually run a hypothesis and you lift an object at constant speed, and you will see that the reading of the scale is exactly the same as it is when it's at rest. Because when the object moves at constant velocity, the sum of the forces exerted on it is zero. So here's another example. You have a loop of wire connected to an ammeter and a bar magnet. You need to describe an experiment that will make the ammeter needle deflect to the right. The needle deflecting to the right indicates the current is flowing into the port on the right side here. So the current is flowing here. Explain in detail what causes the current to start flowing in this direction. So again, they need to design an experiment, and it's an application experiment, and communicate their design and why it will work the way they think it should. So everything that physicists do, we can help students develop if we engage them in certain kinds of activities, and if we put these activities, these problems on the tests, so we assess what they learned. And you might say, my students have never designed an experiment. How can they do this? So what we do, we give them questions that help them, guiding questions, not what to do, but what to think about. And we give them self-assessment rubrics that they use when they are, writing their lab reports or solving problems. So what are the questions? For testing experiments, we ask them to propose an experiment and make a prediction based on the explanation you're testing, not your intuition. So these are the guiding questions, because often students want to predict based on the intuition, not on what they're actually testing. And so these questions help them to focus on the task at hand. And we give them rubrics of how to identify a hypothesis to be tested and how to design an experiment. I won't bore you with these rubrics. They are on this website. If you just Google scientific abilities, you will find tons of them. I don't think we'll spend time discussing the rubrics. But how the rubric is written, we have 3 levels. And 0 is a student just doesn't do it. Inadequate or not adequate level is when a student knows that they need to do something, to write something, but what's written is vague. Needs improvement, the student writes relevant things with some minor omissions. And adequate is perfect as we can expect. It turns out that when, as an instructor, you write a rubric for what students need to do, you realize how difficult it is to tell them what we expect of them. And yet we expect of them to do something we don't even know what. So what do students think of this? So we interviewed students in the class of David Brooks. He came to do a workshop for you a few years ago about IEL. Maybe some of you remember David. So he had a class of 40 students, and about 20 were interviewed. And they asked them questions very simple. Why did you take this class? How does it compare to other classes? Would you like to change anything? When they said something, the interviewer would say, well, what do you mean? Can you elaborate? Can you give an example? So as I said, about 20 students, 9 females and 8 males. So the duration of the interviews went from the shortest were about 20 minutes to about almost an hour and a half. We took the transcript of the interviews, they were videoed and transcribed, and identified the themes that they were talking about. They were talking about group work and experiments and problem solving. So they mentioned from 50, this is the largest number of themes mentioned by anyone, to about 10. Females mentioned more different themes than males, and they talked more. But the number of themes per minute were about the same between 0.6 and 0.8. So about 1 theme per minute emerged from the interviews. So what were the most common themes? The first one was transfer. They were talking that they could transfer what they learned in the class to other classes, to real life, and to their future jobs. So even if I'm in class with the professor like a robot, just talking, reading PowerPoints, I can go home and turn it into something that is going to be interesting to me, because you guys made us think about how we learned and what the best way to learn is. Whereas most students who didn't go through that would probably just be satisfied reviewing notes because they think that's the best thing to do, because they've never really thought about, well, maybe I'm different. Maybe everyone's unique and everyone has a special way to learn. The next one, so transfer was mentioned by every single person who was interviewed. They found the course useful, not just to get a grade in the course, but for other things. They mentioned experiments. By the way, that we learn these things, it's not as hard as what the regular physics students. They're like, oh my God, this equation is so difficult to derive, and this and that. But our class, we're like, well, it's easy, because if you grasp this and you think about the situation when you get this, and it's cool because we got to do all those experiments that we understand already how it works. So they learn by doing and reasoning about experiments. They value the opportunity to figure things out. It was a learning process because I was so used to be fed information and remembering it and repeating it that here at the beginning, I didn't like it because I was not shared information. I said, what the heck is this? How am I supposed to learn anything? The professor didn't tell me anything. And I was so used to, so accustomed to being fed all this information, memorizing it, that you have no idea what's going on. Here, I have to figure out what's going on, and then a true understanding could arise. Affect means personal feelings. I definitely do enjoy physics. I enjoy biology for other reasons, but it is just because I love animals. So it's a different reasons. But in terms of interaction and stuff like that, I like physics a lot. And it really does. At first, I come to class and I'm like, oh, what crazy thing are we going to do today? Let's see what happens. And then when we're actually doing it, I'm just so hyped and I'm so excited. And magnets, you know, I love magnets. My magnets, oh, those are my babies. I love my magnets. Can you imagine your students talking about experiments the way this young woman talked? They also talk about group work, community, confidence, problem solving, and knowing where things came from. And another thing that we found that these students persevere. Grit is one of the predictors of success, most important. We find that designing their own experiments develops perseverance, while doing traditional cookbook labs does not. On average, the time spent by IELTS students making sense of experiments, designing, analyzing data, revising, is 4 to 5 times longer than for the students in traditional labs where they get step-by-step instructions. IELTS students also do well on standardized tests. They use representations other than mathematics when solving problems. They are able to design experiments, collect and analyze data, evaluate assumptions, communicate findings, and the latest dissertation of Daniel Bouget shows that high school students who learn through IELTS remember and apply what they learned even 10 years after graduation. So, is it difficult to implement IELTS? Yes, because instructors need to learn to think about physics and student learning differently. They need to act differently in class. You are not an actor in the center of attention. You are not telling them what it is. You are facilitating, you engaging them in their own learning. So you are not important. What they do is important. The students need to think about their learning and instructor teaching differently. They need to act differently in class. Instead of sitting and waiting for somebody to give them information or an answer, the students have to figure it out on their own. Of course, at the end, after they work for quite some time, come up with their own ideas, the instructor will summarize. The students will share, they will reflect. We have this time in class that is called time for telling. This is when you summarize what students just learned. But in a traditional classroom, the time for telling comes before students had any opportunity to try. They don't have the need to know, and we're already telling them what the right answer is. Lots of research shows that both changing the instructor mindset and the student mindset is very difficult, but this is a subject for another talk. So we have lots of resources to implement IELTS. They're all, unfortunately, written in English, but if you and your students can communicate in English, you can use them. Most of them are free. So it's a big team, and one of the members of the team, Goras Planinsik, will speak to you today in the afternoon. We have the book, as I said. Your library, your university library should have it. It has a PDF edition and a hard copy. We have the textbook, comes with the active learning guide. And now we created online active learning guide to learn during when instruction is online, comes with the instructor guide, and we have a ton of videos that are freely available without adopting anything. This is the resource with videos that is absolutely free for everyone. It's www.ielphysics.net/pt3. It has a lot of videos for special topics and also interesting puzzles and experimental problems. This is the website for scientific abilities, where we have all the rubrics and the labs for real instruction and online instruction. We're posting the labs that can be done with video experiments now. We have the offshoot for middle school and high school physics. It's called PUM, Physics Union Mathematics. All materials are free. You just need to get teacher access. Click on teacher resources and the email comes to me. I'll give you access. And if you are not familiar with this website, it's amazing. It's done by a teacher. And these are the games that are IEL-based. The students can play. About 10 million people so far play these games. It is the website, if you just remember, theuniverseandmore.com. So, few points to take away. First, learning means change. It's the change in the brain and the body of the learner. So if learning involves the change of your neuronal connections, then it's the learner who needs to do the job. You telling them what it is not going to help. As well as me telling you this now is not going to help. But we do this traditionally anyway. Brain cycle proceeds from sensory experiences to reasoning and to motor functions for active testing. What does it mean? It means that when the students are sitting in lecture listening to you, it's only sensory experience. If they do not reflect on what they think and come up with their own ideas and actively test them, and for actively testing, you need the motor function to be engaged. You need to speak, you need to touch, you need to do an experiment. Then you cannot learn. That's why learning gains in traditionally taught courses are very, very small. Scientific inquiry engages people in similar processes: sensory experiences, reasoning, and active testing. IEL is the real path that scientists take. They proceed in their exploration through the same steps as we outline in the IEL process. So students who learn physics through IEL can participate in real sense-making. And the IEL learning system is designed to empower all students to learn physics. It is an example of a universal design for education. Thank you very much. If you want to talk to me, send me an email.
Thank you.
Thank you. I
Eugenia.
will stop sharing, right? So you can see.
Yeah. Thank you so much. We already have 2 questions from the audience. So I will read it for you, okay? From Joel, Philippines. The LSZ, it's supposed to be the school where the affiliation. The activities are very nice and interesting. How long does it take to complete one activity, including the students' presentations, explanation, discussions? Because in our country, science session per day is just 50 minutes to 60 minutes. And we have lists of competencies and topics need to cover within a certain period of time. That's the classic question.
Yeah, that's usually number one question. So activities vary in time, and you can decide if all the students came up with the same answer, they don't need to present. The presentations are only if there are different ideas emerging from different groups. Secondly, the students who learn to think this way, at first the process is slower and then it picks up. Third, when the students learn to think on their own, you do not need to cover all the material in class. They can study and share their ideas, and you only provide the list of questions for them. the point is that when we think that we need to cover everything in class because the students need a list to be covered, remember, then when you move fast, students don't learn anyway. So we start with students not learning much. Our method allows them not only to learn, really learn, but also to learn how to learn on their own. So if you did not have time to do, let's say, angular momentum in class, but you can pose questions for them to answer on their own, and they know how to read the book to discern what experiments were done, how they were explained, what ideas were created, how they were tested, then they learn on their own. And believe me, what they learn on their own, they remember and understand much better than anything you taught them. And how do I know it? Not only because of the hundreds of studies that have been done so far, but I'll tell you a story of how I came up with this method, of how I became convinced that active learning is the way to go. So I taught in Russia for many, many years. I was a very good teacher, and the students loved me very much. And I explained everything very well and followed the process like on the aisle diagram, but I was more or less traditional teacher. So at the end, the students would take final exam and oral exam, everybody. It was a compulsory course. And those who got A's, I thought they really learned. So one of these students came to see me a year after. He got an A on the exam and he got all A's as long as I was teaching him. So he was getting ready to be a theater director producing plays. He came and he was just, excited and said, Eugenia, we learned about a pinhole camera. How pinhole camera works because they use it in medieval theater to project, pictures and the views on the screen. And I said, do you remember we had a lab with the pinhole camera? And he said, I don't remember anything from physics except X-rays. I said, why X-rays? He said, remember, I did a presentation on X-rays. I learned about X-rays on my own, by myself. So that was the value of all my brilliant explanations and great experiments and wonderful problems. X-rays that he learned on his own. I understand that one data point is not statistics, but this data point is one of hundreds of thousands data points that we now have. So I know you are not satisfied with my answer, but that's what it is. Covering more does not mean they will learn more. So what's the second question?
Joe, why I said it is a classic question, because in the beginning I asked the same question. Okay, the next one is Bernatal Saragi from Indonesia. Unmul. I hope I know the what it stands for, but I don't. The question is, building student confidence in research, one of the lecturer's duties. How to build student confidence?
How to build student confidence? That is actually a great question. And I would say whoever asked this question really understands the difficulty in teaching physics. It's the lack of confidence. So how we build it? We actually do it systematically. First, we don't have right answers. So when you observe something, you say everything you see. When you come up with crazy ideas, you don't need to come up with the right ideas. You just need to come up with some idea that you can test. And then if students cannot come up with a testing experiment, which sometimes happens, the teacher already has his or her own. All they need to do is to make a prediction. And when the idea, that crazy idea that I propose, is rejected, it's great, because rejection is a more fundamental answer than the failure to reject, because then we need to test it again and again and again. Confidence is built when people work in groups and they're not put on the spot. When the person who presents the consensus of the group does not present his or her own idea. So even if the group did not solve the problem, it's the whole group, not one person. When you are allowed to resubmit your work, redo and improve as many times as needed, it builds your confidence, and people say, I can really learn, I just need more time. The confidence is built when you know how to start solving a problem, right? Students' lack of confidence, they'll say, I know the theory, I just don't know how to solve problems. Why? Because they don't know how to start. So we teach them how to start. You know, two physicists worked into a bar, and immediately one of them is drawing something on a napkin. What does it mean? It means that the other one asked him a question or her a question, and a physicist immediately starts drawing. So the students need to draw what the problem says. Everybody can draw. So this is how step by step we build confidence. But I think the major contribution to building confidence when you feel that you're part of the community. So when you study together, when you work on problems together, when you do projects together, and you're part of a bigger whole, then you're confident that you belong. And I think it's the women who suffer the most from lack of confidence. I know I do. I still have, you know, the strongest imposter syndrome you can only imagine. So you cannot get rid of it, but you can make people think that I can. Yes, I can. And I didn't show you the student evaluations from, you know, in US, they fill out professor evaluations after every course, and in Canada too. And, you know, one of the courses in Canada that uses IELTS, the instructor sent me student evaluations. All of them talk about different things, but the majority says, I now know I can learn anything. I can do it. So that's confidence. So everything that we do, one of the ultimate goals is building confidence. So all the details, so I suggest that you get our book in the library and read it step by step, and you will see what we do to build confidence.
Thank you, Eugenia. That's a good answer for me. I hope it's also for Benata. The next one is from our colleague with Artika. She's from teacher training and education faculty. How to apply this IELTS STEM approach in biology learning. Oh yeah, she is from biology. What important things that I need to pay attention to?
Well, how
Can
to
you
apply
tell about biology?
Yeah. So we don't have materials, and people ask me, do you have materials for biology? And I said, no, I'm not a biologist. How to create them? The creation of materials starts with knowing history. For example, we want our students to learn photosynthesis, right? So photosynthesis says that the mass of plants, you know, you plant a little seed, a huge tree grows. Where does this mass come from? So where can it possibly come from? Of course, it comes from the soil, right? So how can we test this idea that it comes from the soil? Here's a historical experiment that was performed by, I don't remember the name of the guy, who planted a little seed in a pot, and he weighed the pot. Then the tree grew, he removed the tree and weighed the pot. So if the mass of the tree came from the soil, then the mass of the soil should be less, but it was about the same. So it doesn't come from the soil. Okay, so it comes from the water. So we water the tree. Again, somebody else did this experiment. It takes years, but you can tell them the result. Water, measured the mass of water, and the mass of the tree was much, much higher than the mass of water. Where did this mass come from? So the only thing that is left is air, right? And then who tested the idea that the mass of the plants comes from the air, from the carbon dioxide in the air, right? So that is just one example of how you need to know the history in order to help students figure it out on their own. Designing activities takes time, and biology is different because you can, many experiments, growth takes time, and you cannot just go and open up a person's heart. But somebody already did this experiment. You can have a video, you can have a simulation, but you need to start with the phenomenon. In biology, or in chemistry, or in physics, we start with the answer. We do not start with the phenomenon. So think about what phenomenon students can observe or recall, and how can they explain it. It's a long process, but you can start small with just some concepts. Genetics, the work of Mendel is perfect for IEL because that's exactly what he did. He observed, he came up with an idea, he tested it, right? Work on cells also is great. All, botany is perfect for IEL. So go ahead, make it.
Yeah, thanks, Eugenia. And now from Mikwan, Shakwala University, our colleague too. Based on your explanation, the STEM policy would be more fruitful to students, are not limited to practical resources, modern lab, especially in institution. What are the plan of the STEM system to create an enabling environment for such implementation?
Well, I will tell you that we use very simple equipment that is cheap and very affordable. So if you look at our materials that are freely available, you will see that most of the experiments use simple stuff. So it's not a huge expense. What is important for the implementation of IEL is having these whiteboards. And I actually have one in my house. So if you let me run downstairs, I'm going to bring it. Okay? So let me just bring it. I'll go run and show it to you how big it is. Okay? Just a sec.
Okay. Thank you, Eugenia. That's the type of teacher Eugenia is. She's always trying to showing to the students how it actually works. I sit in her class for 2 weeks, and I can tell that it's really an entertaining classes. While we wait for Eugenia, allow me to tell you about our visit to Rutgers. Hi, she's here. So I don't have
let me try to show it to you. Just a sec. I will put the headphones so you see what it looks like. Oh. Okay. So that's the board. See? This is the bottom, and this is the top. I'm holding it in my hands. And we buy it in the stores that sell tools. And these are the big boards, and they will cut it for you, and you use markers. And that's really important for the students to work together. So these boards last forever. I had mine for 15 years now. So they're like glossy white. You can make them yourself, or you can, get them somewhere. But this is the most important equipment. Everything else you can get in the supply room, and you really don't, like I showed you the experiment with sensors, but you can do it with bathroom scales. You don't need expensive equipment. I don't know if I answered your question.
Yeah, I remember when I visit Rutgers and I visit your equipment room. There's a lot small things there. Okay, so there is a question, but there's no information who sent it. What is the difference between guided inquiry-based learning and IEL?
Well, I think that IEL is a variation of guided inquiry, but there are different levels of guidance. And so what is important in NILE is to guide students what to think about, not what to do. And so when they observe an experiment, like an observational experiment, we ask them, tell us what you see. What patterns do you notice? So this is the guiding stuff. When they come up with an explanation, say, how would you test it? And we teach them what testing means. That you need to design an experiment and you need to make a prediction based on your explanation, not your intuition. We have a list of very carefully chosen observational experiments, so the pattern emerges easily. We are always prepared with possible testing experiments because we know what ideas students will come up with. So our guidance is in being prepared to what students will do and helping them think in a certain way. But we do not guide them what to do. We guide them what to think about. So that's it.
Thank you so much, Eugenia. Our time is up now, but there are from the people who ask questions. Bernardo Saragi from Unmul say that thank you very much, Professor Eugenia Etkina. And from Wiwit Artika, our colleague, thank you, Professor Eugenia. From Akit Harris, say that such an amazing teacher. Thank you, Professor.
Well,
you are an amazing teacher.
Thank you very much. Really,
you inspire all of us.
Really, I enjoyed having you in my classes.
Oh, thank you. I enjoyed that so much. That's why I came here and tried to do IELTS in math. I don't know what I was doing, but I tried. Thank you.
Well, you have a great day.
I would like to say thank you for your support to our program, for our STEM Research Center that is led by Irwandi, Dr. Irwandi. And then I would like to say that what you already shared, you gave us books. I still have the books and everything. You always inspire me to do better.
Thank you.
In teaching. I'm not teaching.
You
said that don't teach.
Don't
I will not teach.
Let them learn.
Yeah.
Let them learn.
Thank you so much for everything.
Yes.
Yeah.
Bye-bye.
Thank you.
Bye.
I hope to see you again. Bye.
Bye. Bye.
Thank you.